In this video, let's look at a couple of operations that we can apply to a linked list. The very first mechanism is called traversal of a linked list. Traversal means moving through data. The idea is that we will start at the beginning of a linked list and move through every single node inside a linked list. This is what we call traversal. In certain contexts, the head of a linked list is usually called head. This is the placeholder for indicating that we are at the beginning of the list. So the name of the head of the list is called letters in this case. So we would like to come up with a temporary variable of the same LL node class, with string being its generic type, that holds the reference address of letters. If letters point to this particular object in memory with a memory address of FA1, then current node, which is a temporary node, will have the same address as what letters points to in memory. So the next one up is writing a for loop, either that or a while loop. As long as the current node is not null, remember the very end placeholder of a linked list is null. So as long as the current node is not null, we print out its get info, and then we iterate through by assigning current node equals current node at get link. So this allows you to jump to the hoops one at a time. At each location inside the node, we print out its info to the screen. That's what traversal of a linked list entails. One, having a temporary variable. The reason why you don't want to use letters simply is because you don't want to change the memory locations of the existing linked list. Because a lot of times you would like to traverse a linked list as a read-only operation versus making changes to the internal memory structures. Think of a situation where instead of using a variable current node as the placeholder to loop through every single node, now you use letters instead. Writing letters equals letter.getLink. You're still able to accomplish printing out every single information inside the node. However, letters will no longer be pointing to 0 times FA1 at the end of your loop. Doing so, your letters would point to a different location. This may not be a desired behavior. So you got to think through what it is you're trying to do with your program. As a best practice, always start up with a temporary variable, assigning it to the head of your list, and then iterate through. Let's break this traversal mechanisms up into steps. Here we see the use of current node right here. As you do system out print line get info, we see that B is printed. The very next line, current equals current get link. This allows you to jump from the current node dot link, which is the get link, that takes you to the very next one. At the end of your first iteration sits right here. And again, this entire while loop continues, printing out C. At the end of the print, you do current nodes equal current node dot get link. This allows you to jump into the next node again. At the end of D, in the very next line where we have current node equals current node dot get link, your current node now points to null. This exit the entire while loop because this while loop's only good if current node is not null. Exit otherwise. Let's go through these steps one at a time. So part 2 shows the printing of B to the screen. And as we move through the current node, which becomes the very next pointer, we then have info equals C printed to the output. And then next up, we'll have information printed, again, D to the output. And this is where current node becomes null. And this is where while condition is now false, which prompts the exit of your traversal. Let's look at another mechanism that we typically applied to a linked list, and that is insertion. Insertion means the addition of data inside an already established linked list. In the example of the above, where we have letters being the head of the list pointing to B, C, and D, which ends with a null terminator, you can insert data at the beginning of your linked list, as indicated by this arrow right here, or you can insert in the middle portion, somewhere in between the beginning or the end of your list. And then you can also do insertion at the end of your list. So these are the 3 generic or general cases we typically observe when you insert data into a linked list. Let's look at the example inserting data at the beginning of the linked list and see how that works. This use case calls for the insertion of data at the front of your linked list. the very first thing we need to do is to create a new node. This could be done by writing ll new node, string new node equals new ll node string. What we want to do is to insert this new node in between letters, which is the placeholder for the very first node and the very first node itself. So we want letters to be pointing to new node and this new node pointing to the original first node. Let's take this to the next step with the illustration. After the new node is created, the very next thing to do is to set link on the new node to letters. This effectively points the new node to letters, which is at this location, 0 times FA1. So that link right there that goes from new node to it is critical because this allows us to chain your new node to the original list. But we're not done yet because we haven't fixed this letters, which is the head of the list. This needs to point to new node. Let's look at the next illustration. Repointing letters to new node is easy. It is just a one-line statement saying letters equals new node. Remember, letters is a Java object that references the original location, and now that location is new node. So this effectively severs the connection between letters and the original list, pushing it into new node. And that's how you insert elements at the front of the linked list. The very last use case is really a trivial use case, which is the insertion of a new node to an empty list. Well, this is really the same as just creating one node, ensuring that node is called letters, and that node has a null terminator at the end. Leveraging what we had before, you can simply just have new node dot set link and do a letters. Before you set letters to the new node, you can have it nullified. This is the same as setting this letter to null. As you can see, this is very trivial. The last thing you want to do is to make sure that you have letters equal new node. This entire operation could have been done by writing new node string a. So what this is doing is we're saying this entire instantiation is a new node with a value of a. And since by default, the link variable or member variable sitting inside L node is null, by setting letters equals a newly created instance of this a node, you would have inserted this a node in front of an empty list. So this is a quick illustration of a trivial use case. There's a more complicated case where you have to do insertion in the middle of a linked list, appending the information at the end of the list, and I'll leave you to those exercises offline. This completes the illustrations of linked lists and a couple of use cases where data is inserted into it.